say work, what's the first thing that comes to mind? Maybe a cubicle or a briefcase or that history exam that's coming up soon. But if you're a physicist, work has a very specific meaning, one that has very little to do with spreadsheets or the fall of the Roman Empire. Today we're going to explore that definition and how it connects to one of the most important principles in physics, conservation of energy. We'll also learn what physicists mean when they talk about another concept that comes up a lot in daily life, power. So let's get to work. So far in this course, we've spent most of our time talking about forces and the way they make things move. You need to understand forces before you can understand work, because work is what happens when you apply a force over a certain distance to a system. A system just being whatever section of the universe you happen to be talking about at the time. For example, if you're using a rope to drag a box across the floor, we might say that the box is your system, and the force you're using to pull on it is an external force. So let's say you're pulling on this box system by dragging it straight behind you, so the rope is parallel to the ground. If you're using the rope to pull the box for 1 meter, we'd say that you're doing work on the box. And the amount of work you're doing is equal to the force you're using to pull the box times the distance you moved it. For example, if you pulled the rope and therefore the box with a force of 50 newtons while you moved it 5 meters, then we'd say that you did 250 newton meters of work on the box. More commonly, however, work is expressed in units known as joules. Now, sometimes the force you're applying to an object won't be in the exact same direction as the direction in which the object is moving. Like if you tried to drag the box with your hand higher than the box so that the rope was at an angle to the floor. In that case, the box would move parallel to the floor, but the force would be at an angle to it. And in such an instance, you'd have to use one of the tricks we learned earlier when we first talked about vectors. Specifically, you need to separate the force you're using on the rope into its component parts. One that's parallel to the floor and one that's perpendicular to it. To find the part of the force that's parallel to the floor, that is the one that's actually pulling the box forward, you just have to multiply the magnitude of the force by the cosine of the rope's angle to the ground. You'll remember that we typically designate an angle in a system as theta. So to calculate the work you did on the box, you just multiply the horizontal component, or F times the cosine of theta, by the distance you move the box. That's one way physicists often write the equation of work. They'll set it equal to force times distance times the cosine of theta. And that equation will fit any scenario that involves a constant force being applied over a certain distance. But what if that force isn't constant? What if, say, you started out pulling hard on the box, but then you started to get tired? So the amount of force you exerted on the box got smaller and smaller the further you dragged it. To calculate the work you did in that case, you'd have to count up the amount of force you applied over each tiny little bit of distance. And if you've watched our episodes on calculus, then you'll know that there's a faster way to add together infinitely tiny increments. Integration. So to find the work done by a varying force, you just have to integrate that force relative to the distance the object moved, which would look like this. But force times distance is only one of the ways that physicists measure work. Because you know how we just said that joules are the units of work? Well, joules are often used as the units for something else. Energy. And work uses the same units as energy because work is just a change in energy. It's what happens when an external force is applied to a system and changes the energy of that system. In fact, that's one of the ways to define energy. It's the ability to do work. There are all different kinds of energy, but in this episode, we'll mainly be talking about two of them: kinetic energy and potential energy. Kinetic energy is the energy of motion. When the box was resting on the ground, we'd say that it had no kinetic energy. But once you applied a force and it started moving, it did have kinetic energy. And the energy of the box changed, which means that you did work on it. More specifically, the kinetic energy of an object is equal to half of its mass times its velocity squared. If this looks familiar, that's because it comes from applying both Newton's second law and the kinematic equations to the idea that work is equal to force times distance. So, if the box has a mass of 20 kilograms and at some point while you're dragging it, it reached a velocity of 4 meters per second, we'd say that its kinetic energy at that moment was 160 joules. Then there's potential energy, which actually isn't what it sounds like. Potential energy isn't potentially energy, it's potentially work. In other words, potential energy is energy that could be used to do work. One common type of potential energy is gravitational potential energy. Basically, the potential energy that comes from the fact that gravity exists. If I hold this book about 1 meter above the ground, we'd say that it's got gravitational potential energy, because if I let it go, gravity is going to do work on the book. Gravity exerted a force that moved it to the ground. Once the book hits the ground though, we'd say that its gravitational potential energy is zero because gravity can't do work on it anymore. Calculating gravitational potential energy is easy enough. It's just the force of gravity on the object, so the object's mass, times small g, multiplied by the object's height, or mgh for short. Which means that just by knowing that this book's mass is about a kilogram and that we held it about a metre above the ground, we can calculate its potential energy, which is 9.8 joules. Another type of potential energy that shows up is spring potential energy. Despite its name, it's not a seasonal thing. And yes, I really made that joke. Rather, it's the type of potential energy that's specific to springs. The force of a spring is equal to the distance by which it's either compressed or stretched times the constant that we write as k. This equation is known as Hooke's law, after Robert Hooke, a British physicist who came up with it in 1660. Now, the constant k, also called the spring constant, is different for each spring, and it's a measure of the spring's stiffness. The equation makes sense if you think about it. The further you push on a spring and the stiffer it is, the harder it will resist. You can even test this out for yourself by taking apart a clicky pen and playing with the spring inside. By combining Hooke's law with the idea that work equals force times distance, we can find the potential energy from a spring. It's half times k times the distance squared. For example, if you have a spring with a spring constant of 200 Newton meters and a block is compressing it by half a meter, then the potential energy of the block would be 25 joules. So when something does work on a system, its energy changes. But how that energy changes depends on the system. Some systems can lose energy, and these are known as non-conservative systems. Now, that doesn't mean that the energy that's lost is literally disappearing from the universe, and it doesn't have anything to do with the system's personal politics either. It just relates to one of the most fundamental principles of science, that energy can neither be created nor destroyed. But systems can lose energy, like when friction from the box dragging on the floor generates heat. For non-conservative systems, you can still talk about their kinetic energy or potential energy at any given moment. But conservative systems let you do much more than that. A conservative system is one that doesn't lose energy through work. Say a simple pendulum. When the pendulum is at the top of its swing, it stops moving for a brief moment as it changes direction, meaning that its kinetic energy at that point is zero. But it has lots of potential energy because the gravitational force can do work on the pendulum, pulling it down until it reaches the bottom of its swing. At the bottom of the swing, that potential energy becomes zero because gravity can't pull the pendulum down anymore. But now the pendulum has lots of kinetic energy because it's moving through the swing. And it turns out that at any given point in the pendulum's motion, its kinetic energy and potential energy will add up to the same number. If its potential energy increases, its kinetic energy will decrease by the exact same amount and vice versa. So now that we know how to define work, we can use that definition to help explain another common term that physicists have a very specific meaning for: power, or more specifically, average power. Average power is defined as work over time and it's measured in watts, which is just another way of saying joules per second. Basically, it's used to measure how much energy is converted from one type to another over time. So remember that box you were pulling? We figured out that you did 250 joules of work on the box when you moved it 5 meters. If you took 2 seconds to move the box, then your average power output was 125 watts. You're basically a light bulb. Now, we can also describe power in another way by putting 2 different facts together. 1, that work is equal to force times distance, and 2, that average velocity is equal to distance over time. Knowing this, we can say that power is the net force applied to something with a particular average velocity. If you move the box 5 meters in 2 seconds, then its average velocity was 2.5 meters per second. And we already said that you were pulling the box along with a force of 50 newtons. So the force you were using to pull the box times the box average velocity would also give you an average power output of 125 watts. The 2 equations for average power are really just describing the same relationship. They're just using different qualities to do it. We're going to be talking about power a lot when we discuss electricity in later episodes. It's the best way to calculate how energy moves around in a circuit. But that's a story for another day. For now, our work is done. Today you learned the 2 equations we can use to describe work, and that energy is the ability to do work. We also talked about kinetic and potential energy and how they play into non-conservative and conservative systems. Finally, we found 2 different equations for power. Crash Course Physics is produced in association with PBS Digital Studios. You can head over to their channel to check out amazing shows like The Art Assignment, Idea Channel, and Game Show. This episode of Crash Course was filmed in the Dr. Cheryl C. Kinney Crash Course studio with the help of these amazing people, and our equally amazing graphics team is Thought Cafe.
All right, this will be our last lesson in physics. I'm going to give you some of the same formulas that she just did, hopefully a little bit slower. We'll do some examples and then I will do some examples out of your book. So right now you need to take a moment and make sure that you have your textbook, some paper, something to write with, and a calculator. No, actually, go get your textbook, some paper, calculator, and something to write with. I'll wait. I'll wait. It's not that hard. Go get it. This can make it a whole lot easier than getting notes saying that, oh, I just don't get this. This is pretty simple as long as you've gone through it once. So, all right. Well, if you aren't back now with your stuff, then you can always pause this and go back and start over again. But this chapter is going to be on energy, work, and power. And she talked about all of these things. We aren't really going to get to the power. I'll explain a little bit, but seeing how we have this week and next week, and that's it. I don't think we'll have time to get into the power, so let's get started here. Energy is the ability to do work, and work is defined a little bit different in physics than what you're thinking of, and energy as well. But we'll get to it later, but for right now we kind of need to know that work in physics is force times distance. Now that's not a formula you need to write down yet. You will, but there'll be a little bit more to it with that. So you have to actually apply a certain force, and you have to move something a certain distance. Pushing on a wall, just thinking, taking a test is very, very little work, because moving your pencil and pushing the keys on your calculator, it takes very little force, and you move them very, very little distance. So the amount of work calculated by a physicist in completing a test would be minimal. Whereas you might think, oh, that was really hard work. But physics, it has to be a force times a distance. Whoops. Did I miss it? The unit of energy is a Newton meter, and which makes sense because it's going to be the same thing as work. We're going to relate the two. A Newton is a force and a meter is there, but we don't call it a Newton meter. It gets named after a physicist, Ernest Joule. So capital J is the unit for both work and energy, and it's in joules. And if we do the math on that, we get newtons are in kilogram meters per second squared, and then we take that times meters, we get kilograms meters squared per second squared, which is the same thing as a Newton times a meter. So what a joule actually is the energy that is required to accelerate 1 kilogram at 1 meter per second squared. So that's where we get the unit from. It actually makes sense. We're not really familiar with joules that much as far as what is 1 joule. Whatever, we won't have a chance to do any labs in the next 2 weeks because you're not even here, where you would get familiar with what a joule feels like, how much is that, how big of a unit is that, but that is the unit of both energy and work. Power is one that you will recognize. Joules you might not recognize. Although I was looking at electric fences for my garden, and they have it measured in joules per second, which is what power is going to be in. So they actually, I guess farmers are more metric than I thought they were. Two types of energy that we're going to talk about, and normally there's 3, but with only 2 weeks left, we aren't going to do the springs. Hooke's law and the work done by a spring, 1/2 kx squared. we normally do when you measure the power of some springs, but we aren't going to be able to get to it this year. Sorry about that. That's probably not the biggest disappointment that you've had ending your senior year this way, but it would have been nice to be able to go through that as well. The first one is potential energy due to gravity. Here we have some kind of a pillar or something and a ball, and if I put the ball on top of the pillar, it now has the potential to do some work because it can fall. It has potential energy due to gravity. Gravity will pull it down. That's how a hydroelectric dam works. We pile water up behind a dam and it has the ability to just fall over the dam, and as it goes down through the penstock, spins the turbine, and we can make energy out of it. So just because it's up off the ground, it's going to have some energy. And it kind of goes back to the second law of thermodynamics. All matter is moving to a minimal energy state. And so eventually, you would expect that this would fall back down to the ground. You kind of assume that all the rocks on the side of a mountain will eventually make their way down into the valley, and they'll be at the bottom at the minimum level. So it's all they have the potential to go down. Now, the force at this point for how much energy it has is equal to the weight, which is mg. You already have that on your formula list, that weight equals mg. And in this case, the distance that we're talking about equals the height, which we're just going to call h. So here's your first formula that you need. Potential energy due to gravity equals mgh, which is just force times distance. Mg is the force, h is the height. How high did the object get moved up? So how much potential energy does it have? And it will be in newtons. Mg will give you newtons, h will give you meters, so newton meters or joules. So the first one just has to do with how high above the ground it is. The second one is kinetic energy, and that's the energy due to motion. And I would normally go through and derive this whole thing, and we would use the steps as we go through and use our principal kinematic formulas to find it. I'm going to ask you just to trust me this year. Kinetic energy, here's your second one. Kinetic energy equals 1/2 mv squared. So 1/2 times the mass times the velocity squared. So kinetic energy depends upon mass and velocity, but much more on the velocity because it gets squared. So you can have something with a lot of mass, even going slow, a train. You don't want to get hit by a train going only 4 miles an hour because it has such a large mass that it's still going to move you. You're not going to be able to stop it, even though the velocity isn't very much. On the second part, you could switch it the other way around. It's still dangerous if you have something really small, just a few grams going really fast, like a bullet, can be dangerous because it has a lot of kinetic energy. Very little mass, but lots of velocity. So you don't want to try and stop one of those. So kinetic energy is a mix of the two, but the velocity is more important. I think I did it, yes. Mass will be in kilograms. Velocity squared will be meters squared per second squared, which is the same thing as kilogram meters times meters per second squared, which will still equal a joule. So we still get the same units from this as we did from the potential energy due to gravity. All right, and then we normally go into the potential energy due to springs, but we will skip that. Work equals force times distance. There's no red box around that. Don't write that down yet. Because as the physicist on Crash Course, as she told you, that there's a directional component to this. We need to know what direction the force is going compared to the motion to see how much work. It's moving a distance. Is force in the same direction? Is it part of that direction? Whatever. And the way that we find that is using the cosine. So if we add the whole thing together, there's your formula. Work equals force times distance times the cosine of theta. And this isn't going to be real complicated. We'll go through some of the problems that we do, and you'll see how this works as well. Whoops. Should be there. There we go. And again, force in newtons, distance in meters, and we get joules again. All right. And this is the important part. Work equals the change in energy. You have to do work on something to change its energy. When I lifted that ball on top of the pillar, this is kind of virtual, but if I actually picked something up and I was going to put it on top of something else, I have to do work to put it up there, and now it has potential energy. The potential energy that's stored is exactly equal to the work that I put in, as long as we ignore the little bit of heat that would be generated to put it up there. We're going to say that this is what's called perfectly elastic and conservative measures. So the work that we put in is going to be the energy that we change. So when we lift something, work equals mgh2, the second height, minus the first height. Potential energy at the end minus potential energy at the first will tell you how much work was done. And you can solve for work, you can solve for one of the heights. Mass is going to be, you could, but generally that's not what you do. We can do the same thing with kinetic energy. If you're speeding something up, or if you have to stop, how much work does your car brakes do to bring you from 35 miles an hour to stop at a stop sign? You can calculate the, I think you can, the amount of work that's done. You take the kinetic energy at the end minus the kinetic energy that you had at the beginning. Now if you are speeding up, V2 is going to be more than V1, so you take this minus this, you're going to get a positive amount of work. If you're stopping, V2 is going to be 0, and this will be some positive number, and so you're going to get a negative number. You can do negative work. That just is a direction thing again. Negative work just means you're slowing down or stopping something. So that's just like a negative velocity. It just means that it's changing in the opposite direction. Now we'll just go through. This is all we're going to do with power. Power equals work over time. If you want to put that on your formula sheet, you can, but I'm not going to require you to answer any power questions. And that would be, work would be in joules per second, and joules per second is the unit that we know as watts. So if you have a 60 watt light bulb, it's telling you how much power it's using, how much of the energy per second that's being used up. And the more watts, the more you have to pay. That's why it's kind of nice with the new ones. It says it replaces a 60 watt light bulb, but it really only uses 6.9 watts. So you get the brightness of a 60 watt light bulb, but you only pay for the 6.9 watts that are actually being used. So that's a unit that we're used to. Don't really understand what it is, but we're used to that power comes in watts. All right, this one is where it becomes, we put the two together and it gets to be more useful. If we have the conservation of energy, just means that the initial energy equals the final energy. it can be changed, and there is always in real life a little bit at least loss, usually due to friction, to heat. It's going to be dissipated to an unusable form. We're going to neglect that, excuse me, for now. There's a part in your book if you want to look through and you think, well, you didn't really ask us to do very much this week. I want to learn a little bit more. It will have an asterisk beside it, which means that it's not only for college, because this is a college text, but this is for an advanced class, and it will talk about the energy when everything isn't conserved and how do you calculate that. But we aren't going to go that. And you get to college, the first couple semesters you won't even deal with that. The formula looks like, and if we had more types of energy, we could put them on both sides. Potential energy due to gravity plus the kinetic energy before, when we start, is going to equal the potential energy due to gravity plus the kinetic energy at the end. And I can wait. You can also pause the video if I'm going too fast. So a classic question, you'll do one of these in the assignment that we're going to do. This would be more fun if we were actually going to be doing this in the next week or so. It actually would have been either next week or the week after that we'd go, and you would be sitting on a roller coaster being told to put your hands in the air, and we can calculate how fast at any point, as long as we know one of the variables, either the height or the speed, we can calculate the other. So when you're going to calculate problems like this, the first thing you need to do is to establish what are you going to call 0 for the height. What's the bottom? And normally roller coasters do not go down and actually ride on the ground. They're always up off of the ground. A little ways are part of the support. It might be close to the ground, but it's going to be up off a little bit. But you don't have to go to the ground. You can take and you can just say at any point, I'm going to call the lowest point this roller coaster is going to go. That's going to be 0. That will make your math a whole lot easier. So then if we want to know what is the velocity at point B and what is the velocity at point C, it's a simple calculation using the conservation of energies. So if we know, I can't see where I put them, if we know that, let's say we're starting at a height of 50 meters above the 0, above the lowest point, and at the top, you're not actually ever stopped, although as you're click, 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 you get just to this point, it feels like you hang there, stop for a moment. You don't, but again, having a 0 here, it makes it a lot easier. We can do it without the 0. It makes it a little bit easier, and then you start to go down. We want to know at the bottom what is it going to be. So if we're going to do that calculation for B, then we're going to take what we have here, we're going to take mgh plus 1/2 mv squared equals, whoops, mgh plus 1/2 mv squared, and that's going to be the same for both of them. So for this one, we're going to start at a height of 50, so that would be 50, and we're going to say that the velocity is 0, so that whole section is going to be taken out. We get to the bottom down here, we're going to say that we chose that point to be, this is 0, so that's going to be gone, and this is what we want to know. So we start with that big formula, and then it reduces down. Sometimes it reduces down more than other times. So here we have this is gone and this is gone. So we have mg times 50 equals 1/2 mv squared. Now, it's nice on roller coasters that this next part is true or almost true. The m's cancel out. Otherwise, they would make each one of us have to get on a scale and go to make sure that the roller coaster is going to be up to the mass that we're going to put into this train of cars that are coming over the edge of it. But it should cancel out. If there's a little bit of friction, which there's going to be, and they include a little bit because the wheels have extra wheels down there, some of them are actually called friction wheels, to slow us down a little bit, because otherwise we're going to be flying off at parts, and we like the thrill, but we want to stay on the track. But we're going to ignore all of that friction, and the masses cancel out. So we're going to take g times 50, which I know what g times 0.5 is, half a g, add a couple of, so I know this is 490 equals 1/2, whoops, that's gone, 1/2 v squared. So 2 times 490 is 980 equals v squared. V equals, there it is, square root of 980 equals 31 meters per second. I have to only get 2 sig figs. So 31 meters per second, which is fairly fast. That would be a nice little thrill, times 3.6 times 0.6. That would be close to 68 miles an hour, so it would feel fast. Now, if we wanted to know what is it at C, we're going to do the same process. We're going to start with, we can get rid of this stuff, and I can get rid of, hopefully it'll let me, maybe it will. Get rid of this. Oh, that's close. For this one, now I can start from the same place. Now I could start from B. I know there's going to be 31.3 meters per second here, so I could start here. I could start anywhere, and A is going to equal B, and B is going to equal C, but A is also going to equal C, as long as we neglect any friction. And I know what this one is already, so I'm going to start from A, because I know that this part for A, this is 0, drops out, and I know that this is going to be 490. And over here, this time, I'm going to have, where did I put it? There it is. I found that the height is going to be at 28. Now I'm going to have some potential energy, and I'm going to have some that is kinetic energy, so I'm going to find the velocity. But I'm going to have to put them both in. The m's still cancel out. They're going to be gone all the way through, because each one has an m. As long as they all have a mass, I can cancel them out. So I'm going to have this 490 equals g times 28 plus 1/2 v squared. And again, that's what I want to know. So now I'm going to work this stuff over to the other side. I'm going to take 490 minus 28 times 9.8, 274.4, and that'll move that over, and then I'm going to take that all times 2 to get rid of the half. Okay, so I get that V squared equals 1078. You have to remember that that's V squared and take the square root of it. And that's got to be wrong because we sped up as we went up there. Let me try that again. 490 minus 274.4 equals that times 2. Okay. Okay, so at this point, we're going 20.8 meters per second. So here we were going 31. So here we would say we're going 21 meters per second. Here was 31 meters per second. So we've slowed down, which makes sense because we took some of this kinetic energy and we put it back into potential energy. So here we have potential plus kinetic. Now you could find out, if you wanted to know, you could find out at D, you could find out anywhere. You can't ever have a place where this is going to go down and the next hill is going to come up higher than that level. Because you can't ever exceed this amount, and if we have this much potential energy, we can't somehow turn it into that much potential energy without some kind of a motor giving it a push, adding some work into it to go up there. So that ride up, that first ride up the mountain where it's going, click, 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 and you can hear the motor working and humming as you're going up. All that's doing is putting energy in. Lots and lots of work it's doing is putting energy up into it when we get up here, so that that's the energy that we have to use. But we can never go above this height, and we can't even get to that again because we are going to lose some to friction. So that's how we use that equation. We'll use it some more here. This is where you need your textbook. Turn to page 174. 174. Get out your piece of paper if you haven't been working along. Calculator, because this is one of those things that looks really simple when somebody else does it, but you have to see where it is that exactly you do to get there. All right, so 174, and I'm going to do 3 problems with you, and then you have the assignment that is under the documents area, or on the news page, I'm sorry, where it is. Make sure when you do these that you make them neat, and the answer that you have gets a box or a circle around it. So you tell me this is the number I want you to grade. And that makes for a much friendlier teacher when your teacher is grading, at least it does for me. And partial credit is much more apt to happen if you've made my job easier. So make sure that it's neat and numbered, and you've got a box around the answers that you want. Let's start with question 3. How much work did movers do horizontally pushing a 150 kilogram crate 12.3 meters across a rough floor without acceleration if the effective coefficient of friction is 0.70? Okay, so what is wanting here obviously is a free body diagram, and you are going to move the crate that direction, and you're going to move it 12.3 meters. The forces, you're going to have to apply a force. So the force applied in that direction, and if it's moving in that direction, we're going to have friction going in the opposite direction. And I would, since it's moving that way, I would assign that direction as positive. Now, we're well aware of the fact that the sum of these forces are going to equal MA. So I can take the force applied minus the force of friction, and we're on a nice level surface, so we know that the force of friction, it's on your formula sheet, hopefully somewhere, that the force of friction on level ground is the coefficient of friction times mg equals ma. Now notice we can't cancel out the m's. It's always nice and convenient when we can cancel out the m's, but we can't because there's no mass in force applied, so the m's have to stay. But they are kind. They did tell us that in this case, they say that without acceleration, so a equals 0, which makes that whole section 0. So I can do a little bit of algebra, and the force applied is going to equal mu mg equals 0.7 times the mass, which they give me is 150 times 9.8, and 150, we're assuming a decimal point, so that's 3 sig figs. 9.8 is actually 9.80, but the coefficient of friction is only 0.70, so we're only going to get 2, but I'm going to keep everything that I can here. And I get that this equals, and it would be newtons, 1029 newtons. But I'm asking for how much work was done, so that's my force. Now my equation for work equals force times distance times cosine of theta. My force is 1029. The distance is 12.3 times the cosine of the angle. Now the angle is the angle between the direction of the motion and the direction of the force. So the angle between this arrow and this arrow is 0. So it's the cosine of 0. And before you think, oh, this is easy, because then if that's 0, everything's 0. The cosine of 0 isn't 0, but it's the next best thing. If we can't call it 0, the next best thing is 1. Cosine of 0 is 1, so I just take the 1029 times 12.3, and I get $12,657 joules, but I only get 2 sig figs, so that's going to round up, so I get 13,000 joules of work to move 150 kilograms, which is pretty heavy. 150 kilograms is going to be somewhere around 350 pounds. I'm going to slide it 12.3 meters, which is a little bit further than across the room. It'd be across the room from the windows in the room, if you remember still being in the physics room. Cross that out across the hallway and into Mrs. Combs' room. That, if you got it into there, we would have gone about 12.3 meters. So that's about what 13,000 joules would be like. It would be a little bit less here. I don't think we're going to have a cardboard box on wax floor is going to be less than 0.7. This would be more like moving a wooden crate across concrete would take that much work. Still had to use the free body diagram and then just force times distance and this. The two thetas that you're going to use, if we were saying how much work did the friction do. Now friction is pulling this way and we're moving it this way. So the angle from here to here would be 180, and the cosine of 180 is just a -1. So since we are going without acceleration, you are applying this much doing that much work. Friction is doing exactly the same amount, so because it's not accelerating, if it was doing more work, you would be slowing down, be decelerating. If you were doing more work than friction, you'd be speeding up. So the friction would be doing negative 13,000 joules worth of work on it. So usually it's either going to be cosine of 180 or cosine of 0. There are other ones, and you can look in your textbook at questions where they have number 8, a grocery cart with a mass that tells you what angle you're going. You're going straight, but you're pushing at a different angle, and yes, but we aren't gonna have enough time to go through that. So I'm sorry again, you won't get to do that. All right, second one. Oh, are there any questions on that? I didn't think so. That was pretty clear. Number 5, how high will a rock go if thrown straight up by someone who does 115 joules of work? Neglect air resistance. So here's ground. We're going to call that h equals 0. And here's our rock. And you don't throw it actually from the ground, but we're going to say that it does. It makes everything easier. It's wherever he lets go of it is going to be 0. So maybe, he's standing here and his arm is at this point. Whatever that rock is, wherever the lowest point that he goes to throw it, the lowest point, we're going to call that 0. And then it's going to go up to the highest point up here, and we want to know what that height is. So work is being done on it to change the potential energy due to gravity. So we're going to use work equals mgh2 minus mgh1. But we have wisely selected to use the bottom part as 0. So this height is going to be 0, which means that that whole little phrase of the equation is gone, and our work is going to equal, it's all putting into the height. And again, we can't cancel the mass because there's no mass here. So we're going to have the work equals, they give us that, 115 equals 0.325, which is about 3/4 of a pound. A pound is 454 grams. Let me see, the right one, kilogram. And times 9.8 times the height. So our height is going to equal, 115 over 0.325 times 9.8, which is going to equal, 36.11, and we get 9.803, so we get 36.1 meters. Would be. So we just use the work equals the change in potential energy and just put in the numbers, solve for the one variable we don't know. All right, last one that's a little bit more fun. Turn the page, number 35. We've got Jane looking for Tarzan and is running along, and she comes to She's reaching for a vine that's coming down. All right, and what do we know? She is V1 equals 5.6, that's fairly fast. 5.6 meters per second. And she's going to grab this, and it's going to go up. Then maybe there's a ledge up here that she's going to swing up to, and she's going to take off and go running down here after looking for him. But how high is she going to be able to go is what the question is. So at the beginning, we look at the energies that we have. So we're going to do conservation of energy. There's mgh plus 1/2 mv squared. And at the end, we've got mgh plus 1/2 mv squared. And this is going to equal that. So we can say that. And conveniently, they all have a mass in them, because we're talking about Jane here, and young ladies aren't that crazy about giving out their masses or their weight, so we don't have to know what Jane's mass is. And when she's starting here on the ground, we want to know what that height is. So we're going to call this height, where she's running, 0, which means that that's going to go away. When she gets up here, when she lets go of this at her highest point, she has to be stopped. If she's still moving, then it would still be going up, and we wouldn't have gotten to the highest point yet. So at the highest point, she has stopped, which means that we have no more velocity. So this comes down to, all that we have left from this is 1/2 v squared equals gh. Now that's not, James, that's not a formula that you put on your formula list. That's only in this particular situation. Sometimes she'll be going and she could still be moving and at a certain height, so you'd have the rest of it in there. So this is just each one of them, you figure out your own final equation starting from this original long one. So I can take, well, I'm going to do it up here, 1/2 times 5.6 squared equals gh. So I can just move the g over there, and I get that it goes up 1.6 meters. She will be able to go up 1.6 meters, which is about a ledge about this high, would be coming up as she's running along. So hopefully there aren't any questions on that. You can now use that information and answer the questions that are assigned in the instructions. And then next week there will just be an assessment activity of sorts over this material, and then you will be finished.